Okay, let's dive right into this. Welcome to The Explainer. Today, we're taking on an absolutely fascinating giant thought experiment. We are going to break down the surprisingly real science behind one of Marvel's most iconic heroes. That's right, we're putting Tony Stark's incredible technology under the microscope of modern science to see exactly what holds up in the real world and what falls completely spectacularly flat.
Are answers to questions that keep scientists awake at night. Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown.
So, here is the ultimate question we're trying to answer today. Could a flesh and blood human actually survive inside Tony Stark's armor? Now, we all know Tony is a certified genius, but as we're going to see, engineering the physical suit and generating the power to run it, well, that's merely one half of the equation. Actually, walking away from using that suit in a real-world combat scenario is an entirely different and frankly much more dangerous challenge.
To really figure this out, we need to set the parameters for our analysis. We're essentially pitting two heavyweights against each other, movie magic versus modern physics. We're going to pit the pure cinematic spectacle of flying around and fighting alien armies directly against the cold, hard, logical realities of our physical universe. And hey, we aren't trying to ruin the fun here. We're just using this amazing fictional technology as a really cool lens to explore some very real, very fascinating scientific principles.
All right, let's kick things off with Section 1, Near Future Tech, focusing specifically on building the suit itself.
I want to validate your hopes right out of the gate here, because the surprising amount of Iron Man's gear, it isn't some far-off, impossible magic. In fact, a lot of it is deeply grounded in modern engineering reality. Let's compare the movie tech to what we can actually do. First up, super strength. Physics literally has no problem with this. We can easily imagine a network of small, incredibly powerful electric motors woven right into the fabric of an exoskeleton to boost human power. Second, the computer system, his Jarvis AI. While it's obviously advanced, the human brain already operates at roughly this level of processing power, so physics doesn't explicitly forbid an artificial neural network from doing the exact same thing. And third, flight. Tiny jet engines acting as microthrusters in boots or gauntlets, we essentially know how to build those today. The mechanics are totally sound.
But yeah, here is where we encounter our first massive hurdle. Section 2, the power problem and the arc reactor.
The entire suit, the whole shebang, hinges on the most unbelievable part of the technology, that miniaturized arc reactor sitting right in Tony Stark's chest. We have to ask, is generating that much power in a device that fits literally in the palm of your hand even theoretically possible? To answer that, we got to bring in the big guns. You've probably seen this definition before, Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. This equation is the ultimate tool in physics to calculate the absolute maximum limit of energy you can produce from a tiny amount of matter. Now, we don't know exactly what Tony's fictional reactor runs on, but we can use this equation to find out if the universe even allows for the kind of power he's outputting.
The actual number Tony gives us in the movie is just staggering. He casually states his prototype reactor produces 3 gigajoules per second. That is 3 gigawatts of power. Just to put that into perspective for you, that is roughly the massive, roaring output of a full-sized industrial nuclear power station, all localized inside a tiny glowing circle on his chest. So does the math actually check out? Prepare to have your mind blown, guys. Let's just imagine his reactor perfectly consumes 1 single gram of fuel, a tiny, tiny fraction of a kilogram. If you plug 1 gram into E equals mc squared and multiply it by the speed of light squared, the math tells us that single gram could theoretically yield a jaw-dropping 100,000 gigajoules of energy. That proves that Tony's arc reactor is actually mathematically supported by physics. The universe absolutely allows for that much energy to be stored in a space that small.
Let's see how this builds when he actually uses that power, right? Imagine calculating the energy cost of an extreme stunt, like flying 10 kilometers straight vertically into the sky. If Tony and the suit have a total mass of about 200 kilograms, and they're opposing Earth's gravitational pull of roughly 10 meters per second squared over a vertical distance of 10,000 meters, you just multiply those together. The energy required is 20 million joules, or 20 megajoules. Even if his boot thrusters are horribly inefficient, say only 10% efficient, it barely scratches the surface of the 3 gigajoules per second his reactor provides. So from a power generation standpoint, he has plenty of juice to spare.
Okay, moving right along to Section 3, the unbreakable laws of heat and momentum.
But don't pop the champagne just yet. We've established the suit works perfectly on paper, sure. Now, it's time to confront the unbreakable laws of heat and momentum. Because while Tony's engineering is undeniably brilliant, the simple everyday laws of physics are about to severely punish our hero. Astrophysicist Neil deGrasse Tyson points out a glaring issue. He says, quote, "Fundamental laws of thermodynamics would indicate this and that heat would melt everything, vaporize everything." You see, whenever you generate nuclear-level power, especially locally in a confined space like your own chest, you create massive amounts of heat. Real power plants require giant cooling towers and thousands of gallons of water just to stop from melting down. Generating 3 gigawatts of power without a massive cooling system attached to his suit means Tony Stark would instantly, and I mean instantly, vaporize himself.
But let's pretend his genius intellect found some magical coolant system for the heat. We still have to pivot to an even bigger problem. Does an invincible suit actually make an invincible pilot? We all remember that famous movie scene where Iron Man is flying along, minding his own business, and he is suddenly shot clean out of the sky by a direct hit from a tank shell. The suit doesn't break, sure, but is the pilot inside okay?
Let's break down the physics of that exact collision using the unstoppable law of momentum conservation. Step 1. The tank shell, weighing roughly 5 kilograms and traveling at a blisteringly fast 1,000 meters per second, hits Tony. Step 2. His invincible armor is tough enough that it doesn't shatter. It stops the shell from piercing his skin. But Step 3 is where physics strikes back. That momentum has to go somewhere. The energy transfers directly into Tony's 200-kilogram mass. Step 4. To conserve that momentum, Tony and the suit are instantly and violently pushed backwards at 25 meters per second.
So the crucial point here is the time it takes for that transfer to happen. 25 meters per second is roughly 90 kilometers an hour, basically motorway driving speeds. Now, that doesn't sound too deadly on its own, right? Actually, scratch that. The problem isn't the speed, it's the time it takes to get to that speed. Because the tank shell is moving so incredibly fast, Tony goes from hovering completely still to traveling at highway speeds backwards in less than 1/1000th of a second.
Let's look at what that actually means for a fragile human body. When you're just standing around, Earth's gravity pulls on you at about 10 meters per second squared, completely safe and normal. In a horrendous, high-speed car crash, the human body might experience an acceleration of up to 1,000 meters per second squared. That is generally considered the absolute extreme fatal risk limit for our internal organs. But the math on the tank shell hit, that forces an acceleration on Tony of 25,000 meters per second squared. To really visually hammer home the punchline here, let's compare the fatal human limit against what Tony experiences in the suit. Look at that massive spike. That represents Tony Stark's reality during that tank hit. He is experiencing an acceleration force 25 times greater than the absolute fatal human limit. There is just no way you walk away from that.
Which leads us to a rather grim reality, what I like to call the pasted pilot. It literally does not matter if the suit is made of indestructible magical metal. The suit is moving backwards instantly, and the front inside of the suit is going to violently slam into Tony's soft biological body. Because human flesh, bones, and organs are most definitely not invincible, that incredible acceleration force would literally paste his body against the inside front of his own suit. So how on earth could he survive this? Well, the fictional solution is something like Star Trek's inertial dampers, a magical technology that fakes gravity to push every single molecule in a person's body at the exact same time, preventing the organs from crushing into each other. But we don't have that. The realistic fix? Tony would need to fire incredibly powerful exterior back thrusters at the exact millisecond of impact to blast air molecules in the opposite direction and completely cancel out the momentum before it reaches his body. But as you'll see in the film, he definitely doesn't do that. Which means, sadly, without magic gravity fields or perfectly timed reverse thrusters, his genius invention is actually just a high-tech tomb. Which leaves us with this final, provocative thought to wrap up our explainer today. If the physics of the power and the tech actually checks out, but it's the fragile biology of our human bodies that ultimately fails us, are we better off leaving supersuits strictly to the movies, or will human ingenuity eventually find a way to conquer our own biological limits? It's a fascinating question, and it really shows just how thrilling it can be to apply real science to our favorite fictions. I hope this sparked some curiosity for you today, and made you look at superhero tech in a whole new light. Until next time, keep questioning, keep learning, and I'll catch you in the next explainer.
If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.